here's what we're seeing in this diagram. For tangential speed, we're seeing that if the object is released, let's put a circle here. Let's put an arrow to show the direction where the circle is going. If the object is released at the bottom, like we said, it will move parallel to the ground. But if Regina releases the softball too soon, like here, it'll get spiked into the ground. I'll put the ground here in yellow so we can all see where the ground is. If she accidentally releases it a little bit late, like here, it ends up going upward.
Oh, so it's like tangent lines in geometry.
Exactly. And that's why it's called tangential speed. So when you learned about tangent lines in geometry, it was a line that touches the outer edge of a circle once. This is literally it. This is tangential speed now. So as we spin this object, you hear it, right? Yeah. It's kind of crazy, right? You can hear that? As we spin this, and that has to do with its frequency. As we spin this object, depending upon where we release it, it'll go in a different direction. Okay, sometimes I launch it that way, but I'm going to hit them in the face, so I'm not going to do that right now. But at the bottom, again, it goes in that direction. So you can try it out yourself. And the classic problem is an object spinning, and then the cord is like cut. It's the same thing as me just releasing it at the bottom. Okay, so the desire is the object to move really tangent to the circle, but the body feels a motion outward. Okay, so this is kind of answering your question because you said, doesn't it really go like a northeast angle? And that has to do with the tangential velocity. So depending upon where it would be released, it would go off at some different angle. But again, the object itself has a desire to move outward, which is why it's pushing back inward. When a softball pitcher pitches, what's keeping the object in circular motion? And hand, arm. How about more specifically? The grip I heard is good. The grip. The muscles in your arm, right? Because what are muscles in your arm really? Aren't they just ropes?
Yeah.
Anybody ever think about that? Have you ever looked at the muscular system in biology class?
Yeah.
What do muscles look like? Don't they look like braided ropes, strings, strands all braided together? Where do you think the concept, seriously, where do you think the concept of intertwining layers of rope to make a really strong rope or make a suspension cable on a bridge? It's a bunch of cable braided together, and then those little cables that are braided all together afterward. They're using the concept of the muscular system in your body. People understand how muscles work, and for a long time have been cutting people open and can physically see what muscles look like. Which is why if you're in a medical school, you study cadavers, you study dead bodies to understand physically what it looks like. So the concept of muscle is where ropes are really coming from. Right? Ropes are modeled off of muscles. So it's your muscle in your arm and your body that's keeping the tension there. And as George mentioned, the friction between your fingers and the ball are keeping the ball in your hand and your grip. So there's a lot going on in that sense. All right, let's keep going with this concept. So let's look at a first example here. So we've got a simple one with an amusement park riding on a merry-go-round. Okay, merry-go-round, the very basic one with the horse that goes up and down. So it looks like this, right? It's not a Ferris wheel. I'm not talking about a Ferris wheel, but a merry-go-round. There's a horizontal plane. It follows a horizontal plane. A Ferris wheel goes in a vertical plane. Right? The Ferris wheel goes like this, whereas the merry-go-round goes like this. It's important that you understand the concept of horizontal plane versus vertical plane. Okay? Horizontal plane is like literally like your desk. That's a horizontal plane, a planar surface. A vertical plane is like the chalkboard or the whiteboard. So the merry-go-round goes around in a horizontal plane. There are 3 people sitting, and different horses, or on different horses, at different locations, R, 2R, and 3R, from the center. If the floor of the merry-go-round is fixed, meaning that they're not moving, like it's not like the horses are moving at different rates. If they're here next to each other, all the horses are moving together. And if you've ever been on a merry-go-round, which you probably wouldn't remember, or if you have siblings and watch them go on it, you'll see that the horses literally move in tandem, right? They move together. The floors are not moving at different rates. So the whole thing is like a DVD or a CD. Maybe, yes, right? A DVD, okay. Because they don't use it anymore at all.
Vinyl. We use vinyl.
Or a vinyl, yes.
It's cool.
A record. So something with a surface that's rotating uniformly. It's not like part of the surface is rotating at different rates. So the question here says, if the floor of the merry-go-round is fixed, then which person has the highest tangential speed? Which person has the highest tangential speed? So think about it for a second. Maybe spend about 30 seconds drawing a diagram, and again, discuss with your neighbor. Okay, discuss with the person next to you. Try to figure out which of these. The diagram might help if you're struggling with the idea. Okay, so I would recommend doing that first. Talk for about 30 seconds, then we'll go over it. Check the order, see if I actually. Oh, okay. Let me see. I may not have made it yet. That's the problem. So let me see. If I made it, then I'll definitely give it to you. No. It looks like I started making it, but I never finished chapter or section 4.8. I've got everything from 4.1 through 4.7 done. It looks like. Let me see. 4.1 to 4.5 is done. 4.6 to 4.7 is done. Yeah, I haven't added 4.8 to it yet. You're welcome to look at the answers on here from 4.1 to 4.5 if you want to start grading it. And you can just take my laptop, put it down here if it's easy for now. If that helps you. That's 4.1 to 4.5, and then after that is... Am I on something? It's the desk? Okay. And after that is 4.5 to 4.7. But 4.8 is not there yet. All right, diagram. I'm going to draw a diagram. You guys probably have it drawn already. Okay, again, this is not perfectly drawn, but these are the three objects right here. Okay? So we've got three merry-go-round horses with people sitting on them, all rotating with the same rotational speed. They're all moving together, right? They're rotating like this. So which is the highest tangential speed? George, what do you think?
3R, because it has to go the furthest amount of distance in the same time.
Did we hear that?
Yeah.
3R, the horse furthest from the center. And the rationale is right, because it travels the longest distance, arc length, circumference. You've used these phrases in pre-calc, in geometry, arc length. S is the arc length. In pre-calc, you might be using circumference and arc length interchangeably. But it goes a full circumference, but further out from the center. So the red dotted line is absolutely longer than the blue dotted line, which is even longer than the green dotted line. So if we were to rank their tangential speeds, we would say, if I call this object A, B, and C, we would say the tangential speed of object C is greater than the tangential speed of object B, which is greater than the tangential speed of object A. Okay, yes, the one furthest out is greatest. And again, how do you figure out average speed? I'm not talking about velocity, because what would the velocity be if you do a full circle and end up where you started? 0. Yeah, if you recall, that's 0. Remember the whole idea of velocity is your displacement over time. And if I walk around the room and end up back where I started, what's my displacement? 0. But my distance traveled is the circumference of the circle I moved in. So when I look at this, I want to think about the fact that when I'm finding speed, it's distance over time. So really, it's 2 pi r over time. And what's the only thing that's changing? R. Time is the same for all three of these because they're moving together. 2 pi is the same for all the calculations. So the larger the r value, the larger the speed. They are directly related to each other. Okay, the larger r, the larger the speed itself. And because we're talking about speed, if you'd like to, we can put absolute value symbols around all these velocity symbols here. Your textbook has a tendency to use the vector line for velocity and then just put v for speed. So in this section, if I use v a lot, I'm actually talking about speed. I'm probably going to be dropping absolute value once in a while, just because it gets tedious. Okay, any questions on the first example here? On the first example? This is just getting you thinking about what tangential velocity is, okay, what it is. Now, remember that this is with a fixed floor. The surface is fixed that it's moving on. Jack?
Is there any difference between clockwise and counterclockwise, or is it?
In this case, no. But later, yes. Clockwise and counterclockwise matter. But for this, if it moved either way, it wouldn't make a difference in this circumstance. Okay? But it does matter later on. All right, so let's again talk about objects in circular motion. And we already talked about this. I asked you a couple questions. What provides the force keeping it moving in a circle? You said tension for one of them. Morris said normal force for the cup. We said gravity for the moon. Caroline said friction for a car on a racetrack. And all of those answers are correct. So the question becomes, what force provides it in what scenario, really? So based on the problem, you have to think about what's happening. So if it's a rope, you got to think about tension right away. If it's a car with friction in the tires, you got to think about friction right away. So when we talk about circular motion here, we're saying something is keeping it from fleeing the center. Something. And that something is some sort of a force acting toward the center. That force reacts to motion of the desire to move outward. Right? The gravitron. You want to move outward, but the wall pushes you back inward. So when we look at this, and we look at circular motion, and we draw a circle here, and the object is right here at this moment, let's say, and let's say it's moving in this direction, which, by the way, is called counterclockwise. It's not as important yet, but we'll see it later. So it's moving at a opposite the clock, counterclockwise direction, and the object is currently in the upper right portion, that dot there. If I were to draw the velocity of this, it would be tangent to the path. So there's my velocity vector. And that's the direction it would move if I let it go. From spinning an object, let it go when it's here, it'll get launched at that angle. But we just said that the desire of the object, and that, this is not a force that I'm drawing right now. I'm not drawing a force. The desire, the inertial desire at this moment is to move outward. That's the desire. This is not a force, what I'm drawing there in blue. That's why I put a dotted line. Indicate I'm not drawing a force vector. But the force that is actually acting pulls it back toward the center. Put an X to the center for now. Okay? The force pulls it back toward the center. And again, tension, friction, gravity, normal force, whatever it is, pulling it back to the center. What I want you to also recognize, though, is this. Newton's second law tells us where there's a net force, there must be
Equal force in the opposite direction.
Good idea. Ask me the third law.
Oh, I think it was that.
Mass and acceleration.
So if there's a net force acting in a specific direction, there must be
Movement in that direction. Acceleration.
acceleration. One word, acceleration. There's always mass, right? If there's no mass, the object doesn't exist. So the mass part didn't really matter there, George, It's the acceleration. So if there's a net force acting toward the center of this circle, it means that acceleration is acting toward the center of the circle. The acceleration is acting toward the center. Your book does a whole derivation about why acceleration is toward the center using vector analysis with velocities. It gets very cumbersome. It's not by any means too difficult for you to understand. So by all means, feel free to, when you're reading, look through that analysis. But I'm giving you guys a simpler example and a simpler explanation. There's clearly something pulling it toward the center to keep it from moving outward, that centrifugal effect of outward, and we say that it's a force pulling toward the center, and it's that tension, or that gravity, or that friction. If there's a force, there must be acceleration acting toward the center. But you might ask yourself, Mr. Howell, how could there be acceleration? How could there be acceleration if you're spinning it at a constant rate? Right? Let me spin the object again so you can see it. When I was spinning this, I was not speeding it up or slowing it down at all. I mean, I could do that, obviously. You could easily speed it up, right? You could start slow and get faster. But I'm going to spin it at a relatively constant rate, right? I'm not really changing the rate right now. I'm purposely not. Yet I will tell you that there's absolutely acceleration acting. So how is it possible that I could have a constant rate of motion, a constant speed right now, yet have acceleration? How is that possible? Because constant speed, we said in the last chapter, for linear motion, if you have constant speed, your acceleration is usually what? It's usually zero. But I'm telling you now that it's moving at a constant speed or a constant rate, and yet there is acceleration. What do you think, Christina?
Maybe it's because gravity is still affecting it. For example, once on the very bottom, gravity has like its full effect. And like at the very top, the ones on the sides, they're like multiple forces affecting it in different directions.
Gravity definitely plays a role, in your analysis of gravity being different in different spots is really spot on. But it's not the reason for this. So you're right about gravity. Gravity definitely plays a role in this, and it's at different spots, gravity behaves differently here. It's not gravity that's affecting this answer. What is the definition of acceleration again? The change in velocity over time, right? And I told you this was moving at a constant speed.
Because it's a different direction, it's technically a different velocity.
When I let go of that, the velocity vector was that way. But if I let go of it on the side, now the velocity vector is upward. So although the speed when I'm rotating it is constant because the direction it would fly or move tangent to the circle is changing, the velocity is actually changing. So the directional change causes a change in velocity. So again, this is what we're talking about right now. And although this number is not changing in value, it's 5 meters per second the whole time. I'm just rotating 5 meters per second the entire time. The direction is changing. So if the direction changes in motion, the velocity changes. Okay, so it's not a change in magnitude, but a change in direction. And if you recall, we spent a good amount of time discussing what a vector actually is. And we said it's a magnitude and a direction. And velocity is a vector quantity. If I'm moving this way, what kind of velocity do I have? From your perspective, what kind? And if I'm moving this way? So I can move this way with 2 meters per second, and I can move this way with 2 meters per second, and both of the speeds would be 2 meters per second. But my velocity would go from being negative 2 meters per second to being positive 2 meters per second. So remind yourself that velocity can change if either its magnitude changes, I spin it quicker or slower, or if the direction changes. And clearly we can see that if I put this object over here now the velocity vector looks like that. So the direction of the velocity has changed from where it was shown in red to where it is shown in green. So it's the direction that causes acceleration towards the center. Okay? Valentina.
If the outward force, the force pulling it outward and the force pulling it
Careful. It's not force outward.
So
Be careful.
it's just the tendency to balance with the force pulling in. What would that be? What would happen?
That's like a state of almost equilibrium. It's like a state of balance. We're not going to call it equilibrium because it's not like some of the forces equal zero there. But that's a balance between the tension pulling in and the desire to move outward. The inertial effect outward is balanced by the tension pulling in. That's all it is. There's no name for it. There's no specific term. We're going to see how it plays a role with equations. But it's not technically equilibrium there. Okay?
There wouldn't be acceleration.
Say again?
There wouldn't be acceleration in that case.
Well, in that circumstance, if the desire to move outward is balanced by tension pulling in, there is acceleration because the force is pulling in. And if there's a force pulling in, there must also be acceleration. Now, if this force pulling in that was needed to keep it in circular motion was too great, the rope would snap. That's what would happen. So if the desire to move outward is greater than the maximum tension that the rope can withstand, the rope will literally snap. It'll tear. I'm trying to think of an example of this where you may see it. Here's a good one. It's such a cool thing. The invention of genius. So you ever see this new water balloon thing where you can fill up like 30 water balloons at once?
Yeah.
You know what I'm talking about?
Yes.
And then you kind of like just shake it and it'll pop off that little thing and it like ties itself.
Yeah.
Imagine,
themselves on.
what's it called?
As they fill up, they just pop themselves on.
So imagine they didn't pop off though, right? And they were just attached to it with a little bit of tension there. If you started to spin that at all, they would all fly off in different directions, right? All those little water balloons would fly off because the allowable maximum tension that it can withstand would be exceeded by the desire to move outward. Okay? Another example that would be not obviously a good thing at all would be something like you're going around in a roller coaster and you're going through a roller coaster in a loop, like a loop-the-loop, those things that loop around. It's one of them right over there in the ground, I think. Right? That little loop. Look, gonna hold it up more. So as you're going around a roller coaster and you go around the track and you're at the top, the track pushes back against you to keep you in circular motion. But if the track were to fail at the top of that, the object, you, would literally be launched vertically out, upward. That's what would physically happen. So in this case, it's the amount of normal force provided by the track. If the normal force needed exceeds the strength of the track, the yield strength, the track would literally break, and you would then fly off tangent to the circle. You would no longer be in circular motion. The same concept applies with tension in the rope. Okay, same concept. We're going to get into more of these formulas to see a little bit more. So let's keep going. So let's look at our formula now. So our formula for centripetal acceleration here, centripetal means, by the way, center seeking. Center seeking. And I usually don't write a lot about this, but I wrote here, this is not to be confused with what I talked about earlier, the centrifugal effect, the desire for this object to move away from the center, to move outward. That desire that you feel on the gravitron. These are very different things, but they do what to each other? They balance each other out. Again, it's not called equilibrium, and I'll explain why that is, but it's like equilibrium. Okay, it's very much like that concept. So in this problem, we look at the formula, this statement here, we look at the formula. And we call this centripetal acceleration and say that it's equal to your speed squared over r. That v is speed. Write down speed there, please. That v is speed. Okay? Speed in this case. If you want to put an absolute value around that v, you can. But for all of these problems, I'm not going to be putting absolute value every single time. So when we talk about centripetal acceleration, you got to know that that's speed that we're talking about in the numerator. So it's clearly a function of your speed. So if it's faster, your acceleration needs to be greater. So for example, when I said earlier I could spin this faster and you start hearing that noise, when you start hearing it, you're hearing the air resistance against the actual mass of the object, but it's moving at a faster rate. So the tension in the cable is now much greater. If I slow it down, there's not much tension. Look, I lose tension. Are you all saw that? The cable has slack in it at that point. Slack means that it's not taut. This is a taut cable. This is a cable with slack in it. So if I spin this too slow, it eventually doesn't have tension in it. But if I spin it fast enough, it'll keep tension. And if I spin it faster, there's more tension. So for there to be more tension, there must be more acceleration. Because F equals ma. So the force of tension is really just mass times a, but a in this problem is now v squared over r. So if I increase v, I'm increasing the acceleration. By increasing the acceleration, I'm increasing the force that is used here, or therefore increasing the tension here. Now, watch what I'm going to do next. I can take this and make it much smaller. Make the radius a lot smaller, like this, and spin it like this. Now, when I spin it like this, to do it, what am I doing? I'm decreasing r a lot. So if I decrease r, I'm also increasing a. Because those are, how are they related? A and r. Inversely, or indirectly, right? If I increase r like this, I'm now trying to spin it just as fast at the same v, but the acceleration is far less. The acceleration is far less. Because again, they're indirectly related, so an increase in r yields a decrease in the acceleration. So understanding the relationship between these variables is key for this problem, or for these problems. Let's take a look at an example. A car moves around a circular track at a constant speed. It's a plug and chug here. If the radius of the track is 20 meters and the centripetal acceleration is 6 meters per second squared, then what is the speed of the car? And what is the speed of the car? So let's start by listing our givens. No need for a free body diagram here, simply because we're not looking at forces just yet. When we get to forces, we'll include free body diagrams. So we have the acceleration, and that's the centripetal acceleration, given as 6 meters per second squared. We've got the radius of the track as 20 meters, and we're trying to find the actual speed of the car. So again, I said it's a plug and chug because you're literally just plugging in and going through the problem. So we've got AC equals v squared over r. Solve this for v. AC times r equals v squared. So v equals the square root of r times AC. So a simple problem, but a problem that you might need to actually determine the answer to before you can move on to the next part, which will be forces. Okay, so we have to understand how to determine acceleration or velocity or radius as a function of one of the other two or two of the other three variables. So that would be velocity or speed in this case. So the square root of 20 times 6 is the square root of 120, approximately 10.95. Okay, I'm plugging in what was given earlier in the problem. Okay, what's given here and what is given here gets plugged into the formula for these two spots. Okay, around 10.95. I just want you guys to recognize that this formula, although very simple, can be used earlier on in a problem as like a part A, which then leads into part B, which leads into part C, kind of one of those problems where it steps you through each part along the way. Questions on examples 1 or 2? Questions on examples 1 or 2? Alrighty, example questions, yeah.
Do we have to memorize that, or is it on our?
Let me check. I think it's on your formula sheet. I think it says AC or AR. Some books call it AR for radial acceleration as opposed to centripetal. Either are acceptable. You see both of them? What do you got in the front of the sheet? You see a V squared over R anywhere? Yeah, it's there. It's on your formula sheet. So this formula right here, okay, is listed on your formula sheet. All right, so now let's talk about this concept of period and frequency. So period and frequency. Where have you heard the phrases before? Period, frequency? Where do they play a role? Give me something like that. Oh, freak out. You done already? Talk about it? Nice. Perfect. Perfect. That's great. So, the period is the time it takes to complete one cycle. The frequency is the amount of cycles in a
Period.
frequency. The amount of cycles in a second. In a unit time. In a second. Revolutions per second. Radians per second. Frequency is how many times something like a wave oscillates back and forth. You jump off a diving board, you go in the pool. What does the diving board do? It goes and eventually stops. It's a fin. It acts as a fin or a blade. Or something rotates. The rate at which it rotates. If it rotates 1 revolution every second, that's its frequency. A revolution per second. A revolution per second. What if it rotates 2 revolutions in a second? That's a higher frequency, a higher angular speed or angular velocity we're going to see later. So this concept of period and frequency shows up a lot with circular motion. So I'm going to introduce it to you. We're going to do a lot with this a little bit later in, I think it's like chapter 8 or 9. But I'm going to introduce the concept first here because it plays a role. So first, the term frequency is measured, the term frequency is measured or written as F. Okay, and the term period is written as T. F is frequency, T is period. God bless you. Frequency in your pre-calc course is in radians per second. All right? Radians per second. In physics, you're not going to see it in radians per second. It's going to be in what's called revolutions per second. Remember what brackets mean when I use brackets a lot? I'm talking about the units themselves. So frequency is revolutions per second. So, for example, if an object revolves at 4 revolutions per second, what would the period be? If it was 4 revolutions every second, what would the time period be for 1 revolution? If it's 4 revolutions every second, how do I find the time period for one of them?
A quarter of a second.
A quarter of a second. And let's think about that logically, right? In 1 second, it goes 1, 2, 3, 4, all in 1 second, right? So how long did it take to do one of those? We just divided it by 4. So really, what George just derived in a sense, or stated, was that the frequency equals 1 over the period, or the period equals 1 over the frequency. You guys have been probably using 2 pi over f, right, in your pre-calc course? And why do you think you're using 2 pi? What units are you measuring yours in? Radians per second. And I'm using revolutions per second. Okay? So you'll notice the difference in the formula. It's slightly different. 2 pi is what? The circumference of a unit circle. Goes all back to your unit circle in pre-calc. A lot of it goes back to unit circles. So, these 2 formulas are interchangeable. Because what can I just do? I can switch the positions. I can multiply up by t and divide by f, and I get this formula. So both of those are acceptable. Valentina, is that your formula sheet also? Or no? You have it. See if it's on your formula sheet. It is. It is on there, but it's later on in the formula sheet. It's not where you would expect it, okay? It's later on in the formula sheet. You'll see it further down. And it gives one definition as 2 pi over omega, which is in radians per second. And it gives the other one as 1 over f, which is in revolutions per second. This is the formula we're going to really use in physics a lot right here. Okay? Later in the year, we'll talk about radians per second. We'll see how that plays a role as well. Okay, so good to know, good to keep this in mind. Now, why are we doing this? Why are we adding this concept in where it doesn't seem like it plays a role? Here's the reason. A lot of problems are given where an object, its rotation, its revolutionary speed is given in revolutions per second. It's not given in a velocity or speed. So if I know the amount of revolutions per second, I can somehow convert that into meters per second. So let's talk about how to do that. I'm going to just zoom out a little bit to add a little more room here. So if I think about what velocity or speed is defined as, in this case, for these problems, speed is distance over time. Right? Speed is distance over time. So, for a lot of these problems, what you're going to be given is you're going to be given the actual frequency. And then you have to figure out what the time period is and then figure out what the speed is. So what did we say the distance traveled is when you're traveling in circular motion? 1 revolution is equal to what? What's 1 revolution in distance equal to? Circumference? What is it equal to? No, circumference? Right now? Come on. 2 pi r, 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 pi d, either one. So the distance traveled is going to be 2 pi r. That's how far an object would travel when spinning in a circle in 1 revolution. 1 revolution is 2 pi r. It's the circumference of the circle. The time it takes we call the period length. So the capital T. So we could also replace this with 2 pi r and 1 over f. Because T is equal to 1 over f. So this is a common way to see it. And as a result, it may be useful to use this formula as S equals 2 pi r times frequency. Either of those boxed-in formulas can play a role when you're trying to find out the tangential speed of an object that's not given. It's only given as the angular speed in revolutions per second. So if revolutions per second is given, you can't just use that for your v value in the formula. You've got to go ahead and figure out that this is, by the way, S I'm writing here is speed, or v. You can put v in here if you'd like to. That's going to go into our formula for AC. So let's take a look at an example of that and how we can figure it out. On the next slide, we see a 200-gram object at the end of a string is revolving uniformly in a horizontal circle of radius 0.8. The ball makes 2 revolutions in a second. What is the ball or the object? I said ball or object interchangeably. What is the centripetal acceleration? Where'd that thing go? Did I put it over there? The rubber stopper, is it in there? It is nice. Okay. So the question is, what is its centripetal acceleration? So how are we visualizing this problem? Show me with your hand. Good. Jack, what'd you do? Yeah. So Jack will like this, and Caroline will like this. Either's fine. Okay. A horizontal circle is this. Right? It's like you're a cowboy spinning. You messing right now? Just let it go. It's rubber. It's not going to hurt anybody. So, it's a horizontal plane, a horizontal circle. So we know in this case it makes 2 revolutions. Give me like one more sec. It takes 2 revolutions in a second. What is that? Just so we know. What variable? If it's revolutions per second. Is that a time period? So what is it really? It's the frequency. Okay? So this is the frequency here. So for this problem, when we go to figure out the centripetal acceleration, which is v squared over r, we're going to have to recognize that if we want to find v, it's 2 pi r times the frequency. That's really what it is from the last slide. We derived this formula on the last slide, 2 pi r over t, or 2 pi r times f. So we're given this problem as 2 revolutions per second. We could plug that value in for f. Okay, this is the value of f right here. The radius is given as 0.8. You could square every term here, right? 4 pi squared, r squared, s squared. One of the r squares can cancel here, and you can be left with simply an r, or plug in into all of these variables to get a. We're going to pick up next class with this. Again, homework is 5.1 to 5.3. Read it, please. Okay? Have a good day, guys. And if you want to, I'd really focus on 5.1 and 5.2. 5.3 you should read still, but we're going to get into 5.3 a lot more in the next class. Okay? We're doing today. So this is where we left off yesterday, right? Or 2 days ago, rather. 2 days ago. You were given the frequency. I got 2 open already. Can we open another one, please? Yeah, I'm fine with that.
This room has been hot in the past.
It's not my control, I promise. Yeah, here.
Yeah. Did you host you that class?
No, don't. I just can't. If we have the heat and the AC, it's 2 forms of energy. If we want to open the windows, yeah, go for it. It's cool enough outside at least. Like, we shouldn't even be opening windows when heat's on, but trust me, I understand.
That's on too.
All right, anyway, so we were given the frequency We're given the frequency at which this object is going around on a string in a horizontal circle, right? So this is not the one we were just doing, simply because although this is going around in a horizontal circle, right, the pig was, the tension was at an angle like this. Right, the tension was at an angle. And before the boys came in from their wonderful lecture they just received, we measured the angle, actually. We measured the angle from the normal, or from the vertical in this case, right? So when the pig was about here, when it was flying, it was at an angle of about 30 degrees. So we're going to see that in a little bit. We'll utilize that information, about 30 degrees. But we got to finish up example 3 still, so let's quickly do that. So we talked about frequency, and we said how frequency is really 1 over the period, right? 1 over the period. So if we recall, when we look at velocity, if we want to figure out the, or rather in this case speed, we say it's the distance traveled, which is around a circle, over the time period. And if you recall again, that's 2 pi r over 1 over f. And when you divide by a fraction, remember to multiply by the reciprocal. So this becomes 2 pi r times f. Okay, again, this becomes 2 pi r times f. So that's the velocity, and that value is what's going into this formula right here for velocity. So that value gets squared, all divided by r. If you want to reduce, this is going to be r squared, that'll be r, those will cancel, at least one of them. Then you have f squared and 4 pi squared. So as a result, I don't think I wrote a number down, I should have written one down. Anybody got a number for me by any chance? Can we calculate it? Let's see, the radius is 0.8 meters, let's highlight those. That's going to go in for r. The frequency is 2 revolutions per second. That'll go in for f. And that's all we need to calculate a. So we did not need, if you notice, we did not need the mass. Why do you think we didn't need the mass here? Why didn't we need the mass? Where would mass maybe be used in a little bit? We're finding acceleration right now.
If it's like going a circle but vertical, like on a vertical plane.
Hold off on that thought. You're a little bit ahead, but it's kind of right but kind of wrong right now. Okay? Yeah, if we were looking for a force, and then Jack, if we were in a vertical plane with forces, then mass would apply. But even if we were in a vertical plane, mass would still not apply for acceleration right now. But if we were looking at the force, then it would be. Okay? So when we're looking at forces here, we'll start to apply and use mass. Okay, we'll use mass a bit more. Can I get a number for this? I don't have anything written down. Can I get someone to calculate so we have a agreed upon value? You got it more?
I don't know if this is right, but I got 126.3.
126.3. I saw a nod from Vinny. I'm going to trust you guys are right, and we're going to move on. Okay, 126.3 meters per second squared. Again, my units are the same units as acceleration has always been, except now, again, it's not a change in velocity that's causing the acceleration, or it's not a change in the value of velocity that's causing the acceleration. It's a change in the velocity's direction. Remember, it's the direction tangent to the circle changing. My hand is the velocity vector, and it's changing direction. And as it changes direction, that implicates that there must be acceleration. There must be acceleration. I'm guessing it's going to be Alex White or something? Or?
No, it would be Del Franco.
Del Franco?
The computer like that.
That's right. He's in 403 right now. 401. Alex, wrong airplane. But Del Franco's trying to airplane at 401 and it's stuck on the screen. I can't use it now. I actually can't use it. It's gone.
I don't know. He's like, not no.
1 second and it's just take a flying, like, express the
Don't do that.
yeah, I like on it, just getting such area, but like,
Oh, it's fine.
What's funny, you know how you got the ink from this one?
Alright, sorry about that. Let's go on. So, the next slide we're going to start talking exactly about what we had just spoken about. Forces. So, force equals mass times acceleration, right? Net force. So in this case, the net force is acting towards the center. Again, centripetal, center seeking, centripetal. So the net force is ma. So all we do here is replace a with the formula for a from the previous slide, v squared over r. So this formula is not something that you're going to be given on the formula sheet. Again, you know this and it's given on your formula sheet. You also have this on your formula sheet right now. So you're not going to be given this on your formula sheet. You have to be able to make the substitution from b squared over r in for a. And that's a very simple substitution. Okay? So again, take this right here and substitute it in for a right there. And you can derive, in a sense, it's not a derivation, it's a substitution, but you can show where the centripetal net force comes from here. So let's go to the next slide because we want to talk about where these forces are supplied, what they're supplied by. So we've got a couple scenarios we've already spoken about. The first one, an object swung around on a rope. The centripetal force is provided by what force again? Ft, tension. I'm going to put the word, and then I'm going to put the symbol that we would use for it. The car traveling around a circular track, what's keeping it from sliding out from the circle? Friction. And for this one, I'm going to specify it's static friction, which is odd because you're like, wait, it's moving, Mr. Howell, right? It's moving, isn't that kinetic? So we're going to talk about why that is, but to give you a general overview, the wheels, as they turn, make contact with the ground. And that small amount of contact is not actually sliding or moving. It's gripping the floor as it rotates. If you were to slam on your brakes and the car started to skid or slide, then it becomes kinetic friction. But this is static friction. A roller coaster, Karen, again.
Does like the car traveling like have to do with like, you know, when it's going in the circle, it's like moving forward, but it's not like moving out? Is that why it's like static?
Yep.
Okay.
Because the static friction is preventing it from moving left to right.
Right.
So it's preventing lateral motion. Yeah, it's moving forward and back, and that's because it's rolling. But the static friction is preventing left to right motion. It's not sliding out. If it started to lose track and slid off the road, like the car just careened off the road like that, then it would be kinetic friction.
Okay.
Right? George?
Is the roller coaster normal force?
Yeah, very good, George. Normal force. Very good. That's a tough one.
I have a
Okay.
question about that though.
Yeah, go for it.
Sorry. So why is there normal force if it said in the textbook that it's never actually pushing out? Like there's no push.
Remember, what are you feeling out? You're feeling inertial effects. You're feeling the desire, the centrifugal effect to want to move outward from the circle. So the normal force is combating that.
Okay.
It's really mv squared over r is that desire to move outward. And we'll talk about how that plays a role in the formula in a minute. Okay? And we're going to also talk about how normal force is very unique based on whether you're at the top or the bottom of the roller coaster. It changes. Okay? And we'll talk about weightlessness when normal force becomes pretty much zero. You feel weightless at the top, and that happens on roller coaster rides. How about a stub devil when they're doing like a loop-de-loop with airplanes? What do you got?
Gravity.
Gravity definitely plays a role. There's a couple forces acting. So gravity is one. What else? What else? Imagine like those, you know those, they're called the Blue Devils, right? They do all the stuntings in Jones Beach. Yeah.
Air resistance?
Yeah, and more specifically than that, Jack. You're right. Air resistance plays a role. But in aerodynamics, what are those forces called? Anybody know? There's specific names for them.
Thrust, lift, drag, and weight.
What is it?
Thrust, lift, drag, and weight.
Yeah, so it's lift, drag, and thrust force. Yeah, from the engines. Very good. So specifically here for these, we're going to say lift, drag force. Lift literally lifts off. It's the air pressure that's lifting the plane up. If you take the engineering course, maybe next year, you might talk more about this with me. We're going to talk about heat transfer fluid mechanics in that course. We'll talk about lift and drag. But that's what's generally providing that push. And drag force is providing it to slow down, right? That's a resistance. And yes, we have gravity also. So this is a whole slew of things. And yeah, the thrust force from the engine. Okay, so the actual, what do they call turbines? The turbine itself pushing the plane forward is helping. So this is a combination of forces here. Would probably simplify it a bit if we were doing it for a problem. We would say the overall force is this, or we talk about what force matters most and use that. But there can be multiple forces causing circular motion. How about an electron in orbit? When it's in orbit? From chemistry, what was that force called? Yeah.
Of course, but like pushing it forward to the like towards the neutrons and the protons.
Yeah. It's, you could say the electric force or the electrostatic force. Electric or electrostatic is fine. Okay, electric force or electrostatic. So there's a separate type of physics called electricity and magnetism, in addition to what we're covering, which is called mechanics this year. And in electricity and magnetism, you talk about things like a proton is fired into a magnetic field or into an electric field. Why does it start to curl and turn? That's how these new, like, what are they called? They're called rail guns. Have you heard of a rail gun before? If you play video games, you've heard of a rail gun? A rail gun uses electric and magnetic acceleration to accelerate something forward. So when a particle that's charged goes through an electric or magnetic field, it starts to turn and move as a result of feeling some electric or electrostatic force. And last, the satellite in orbit. Satellite in orbit, the last one. This should be the easiest one, yeah. Gravity. Okay? Again, gravity. So we have variables for most of these. I'm not putting them down for the sun devil because there's a bunch of them. Okay? But those are the main variables that we would be using. So here's my point. Here's my point. FC, on the previous slide, FC is not a real thing, meaning it's not a force that we actually are going to use. Something takes the place of FC. Again, something takes the place of FC. So when I'm spinning, it's back away right now. When I'm spinning something around that's on a cord, like we did yesterday, and when I'm spinning this around in a vertical circle, right, not a horizontal, I'm going to do vertical for now, the tension that's pulling toward the center is providing FC. Now, the weight of this little mass at the bottom, this bob, we call these bobs on a pendulum, this bob, I know her name, at the bottom has weight which pulls down, and the tension pulls up. Now, in this section, we don't care about up or down, we don't care about left or right. What we care about is what forces are acting in the center or to the center of the circle, which are helping it stay in circular motion, and what forces are acting away from the center of the circle. So I'm going to jot something down here. This sum of the forces now, we're going to say this for all of these problems. This sum FC, that gets replaced by whatever force is applicable in the problem. So for that example a moment ago, I'm going to draw my free body diagram. Here's the mass itself that I was swinging. Here's the weight pulling down on it. Here's the tension force pulling back up. And I'm drawing this at the bottom of the path, okay? I'm drawing it at the bottom of the path there. So when I'm spinning that mass around over and over, tension pulls toward the center. Because without tension, this object would move away from the center. But gravity always pulls down. And in this moment in time, gravity pulling down is out of the circle. So for this scenario right here on the right, this sum of the forces would be Ft as a positive because it's acting into the circle. So into the circle is positive, out of the circle is negative. So we then put minus Fg, and that equals mv squared over r. It's not about up or down. This is a coincidence that Ft happens to be up and Fg happens to be down, where it is now. Because what I'm going to do next, watch what I'm going to do next, in blue, I'm going to put the object up here now. And you probably read about this, right? When the object's at the top, now the tension still pulls toward the center, God bless you, but so does the weight. At the top, both forces are pulling toward the center. And that's only because weight always pulls down. Weight always pulls down. Weight always pulls down because it's really a force due to gravity. So as a result, we know that it has to be helping the tension force. Hey, Jen. He should be down the hall. Did you see Spencer in the classroom down there? So they're with recitation with Alex, though, Frank. Not actually in that class right now. 401, yeah. Okay, bye. So at the top of the path there, the tension is pulling back toward the center, but gravity, the weight of it, is actually also helping it stay in circular motion when it's at the top. So the formula at the top is slightly different. The beginning is the same, sum of the forces equals mv squared over r, but now since both forces are acting into the center, this becomes Ft plus Fg equals mv squared over r. Okay, so I used a different font or a different color so you guys can see that. This, again, has both of those forces acting into the center, so we call them both positive. And look at this. Here's where I want you guys to see what I was talking about, the centrifugal effect. This right here, mv squared over r, that's the centrifugal effect. And what is it balanced by in this problem? Both the tension and gravity when it's at the top. But when it's at the bottom, the centrifugal effect wanting to move outward, isn't that in the same direction as gravity when it's at the bottom? They both pull outward. And if I moved gravity over, wouldn't it be helping the centrifugal effect? Use logic here, use your algebra. If I were to add this over, it becomes a positive Fg over here. So with the bottom scenario, the weight is actually not helping it stay in circular motion. It's actually causing it to want to move out of circular motion. It's causing it to want to move away from the circle, the weight of it, which is why when you move it over, it'll add on to mv squared over r. So put a little dotted circle around mv squared over r and jot down that that is really the centrifugal effect. It is not a force. Again, this is not a force. This is the centrifugal effect. Go ahead.
So does that mean that Ft is greatest at the bottom?
Let's think for a second. At the bottom, we would calculate it more by moving Fg over, and these two would be added together. But at the top, we would subtract Fg, so you would subtract the two. So yeah, at the bottom, Ft is greatest. Good point there, Mauro. Really good point. It's a great multiple choice question, right? At what location in the path of this object is the tension force the greatest? And the answer is at the bottom. And that's because if you solve for Ft at the bottom, in black here, you would add Fg over. And there would be an additional value, so Ft would go up. Whereas here, what would you do with Fg? You would subtract it over, right? What does this remind you of? What is it analogous to? Come on, let's see who connects the dots here. What is this very similar to? What classic problem we've looked at a couple times? We've talked about another problem. Another problem. Only one person's got it right now? What do you think?
Is it the outward though?
Which one?
The outward?
Not the outward. Good stab though. Not the outward. What is it similar to?
It's like similar to like normal force.
Say it.
Like normal force.
Yeah?
Then like the two and add the contact.
Like the normal force, you're totally on the right track. And I'm talking about a specific scenario though. What problem? I said, oh, this is a classic physics problem. You should definitely know it. I called it a certain problem. The elevator problem with normal force. If you solve for Fn, very good. You solve for Fn in the elevator problem, sometimes you add the MA, right? And other times you would subtract the MA. Those that did the extra credit definitely should know this, right? You're like, oh yeah, I remember that for sure. Right. Sometimes you added MA, sometimes you subtracted it. Same concept here. It's like the elevator problem. Very good. That's why in physics we talk about modeling. A problem that looks nothing like the elevator problem has a very similar solution where you're either adding or subtracting something from the overall value. Instead of Fn though, it's Ft now. Okay, very good, Vin and Isabella. Very good with that analogy. All right, let's keep going. Example 4. During Project Adventure, you have to swing on a rope to move between two islands. If your mass is 60 kilograms and the length of the rope is 8 meters, the length of the rope is 8 meters and it can withstand a force of 750 newtons, then what is the maximum speed with which you can swing? So what's the problem here? What's the objective here? Trying to figure out.
Is it to see if the centrifugal effect is greater than Ft?
Yeah. If the centrifugal effect outward is too much for Ft, what's going to happen to the rope? Yeah, and hopefully it didn't happen over there, right? I was actually nervous more about the top because I just clamped it in. So I was nervous that this was going to slide out as it was oscillating back and forth, but I let it go for a while to make sure it didn't beforehand. But yeah, if the rope was too weak, the rope would snap, right? The rope would snap. So let's take a look at this. And where are we? Are we at the top or the bottom of the path? Bottom, right? Bottom of the path. And let's think about that logically before we even go into it. So let's draw a figure first. Okay, here's our object, and it's going to swing until it gets to this location right here. Like a pendulum, right? You got a pendulum right over here. In case you don't know what a pendulum is, here it is. Okay, an object hanging on a mat on another fixed surface, just swinging back and forth, right? This is the pendulum problem right here, and that's what we're looking at right now, the one that's swinging back and forth over there. So, and again, we model things, right? We model things with the idea that, like, hey, a person swinging on a rope. The pendulum swing, the mass swing on the rope over there, the pig on that one. Even though that one was in circular motion, you kind of have that parabolic pendulum-like motion to it. Now, in this one, we want to think about, why is it the bottom that has the problem we're going to look at. Why not here? Why is it the bottom and why not here? What do you think, Christina?
Because the bottom is when the tension is the greatest.
Why? Totally right, Christina. The bottom is when the tension is the greatest. We just made that statement. Why is it not at the angle, though? Yeah.
Because the furthest away is from the center, and like at an angle at the bottom, it like swings better. I don't know how to.
They're both the same distance from the center. They're both r away from the center. That hasn't changed. They're both r away.
Because when it's at an angle, you have to split the tension force into sine or cosine.
Think about tension force and the way it works, right? Here's the tension in this problem, Ft. And here's Fg. So it's Fg you have to split, Jack, but you're on the right track. You have to split Fg into components if you did it at this location. You have to break Fg up into this. You call this Fg in the radial direction, and then this would be Fg in the perpendicular direction. So Fg, because remember, we're looking at circular motion, we want to know what forces act into the circle and what forces act out of the circle. So the tension, we actually don't want to split here. Because if we split up the tension, what we're going to end up having is we're going to have tension acting up and to the right. But we want to know what acts into the circle. And the tension already acts into the circle. So we're not going to split up the tension, but instead we're going to split up Fg. So really, if we look at this, Fg is going to be minus off Fgc, which is only a fraction of Fg overall. So by breaking up Fg into its components, we can see that this formula would have a smaller value for Fgc. And if we look at the general formula, we know this is going to be the formula. Ft minus the weight equals mv squared over r. We just wrote this on the previous slide. Again, why is it minus? Why is it minus? Because the weight is acting out of the circle. But if we were at this location over here, we would have to write a component of that, which would be Fg times either sine or cosine of theta. So instead, we do not use this location over here. We do not use the components. We go ahead and we look at, okay, Fg is acting out of the circle, and Ft is acting into the circle. And this is the location that we are concerned with right here. Okay? Again, this is the part that we care about because it has the full weight that's acting away from the center. So when we solve this for Ft, let's move the Fg over. I know we don't have to do this because we're going to actually solve for V in a minute, but I want to actually show this. Okay, that's what we've got. That's the tension force. So this is the most tension the rope is going to feel. Because if I go ahead and use a component of gravity instead, this is going to tack on either a sine or a cosine theta here. And what do you know about sine and cosine theta? When the angle theta, for any angle theta, sine and cosine theta are always what? A decimal. Very good, Sad. They're always less than or equal to 1. It could be equal to 1. And that's only when the angle is at 90 or 0, which is when it's at the bottom. Okay? So if I plugged in cosine of 30, cosine of 50, cosine of 70, those would all be decimals, which would make this quantity smaller, which means that we would not have the most tension possible. And we're looking at the instant when the tension is the most. That's what we care about here. Because we want to know if it's going to snap. And where would it snap? It would snap when the tension is the most at the bottom. Is it not? You sure?
Yeah.
So in this problem, the tension is given, and we want to figure out the velocity that it can withstand. So we have to really solve this for V. I only solved it like this to show you that point just now. So I really want to solve this formula up top, right here. I want to solve that for V. So let's multiply by R and divide by M. I'm going to multiply by R and divide by M. Let me just actually put it like this instead. That'll equal V squared. And notice what I also did. I'll show it in green. I substituted in for Fg with Mg. I substituted in for Fg with Mg. Your textbook likes to use Mg instead of Fg when it puts the weight, and you can actually do that if that helps. If it makes it easier on you, if you'd rather label this as Mg every time and automatically have the Mg there, by all means, that's fine. Okay, so if you want to get used to doing that, you can. But this would be my solution, and then what would I have to do? Take the square root. Okay? This will give me the maximum attainable speed or velocity as this object swings in circular motion, as the person swings through in circular motion. Okay, I think I have a number for this one. I do. 4.6 meters per second. So what does that mean? This is, again, the maximum speed. The maximum speed. So anything greater than this value will cause what to happen? What will cause to happen? The rope is going to snap. The rope is going to snap. The rope is going to snap. Okay? Yeah?
Is the radius 8 in here because the rope is 8, or would it be like?
Yeah, that's a great point. The radius is 8 in this problem. Very good. And we didn't actually write that down, so good point. That is the length of the rope, which is 8 meters, and that's from here all the way to here. That's R. Okay, in the diagram, that's the radius, or that's the length of the rope. Very good. Okay, and then the mass is 60 kilos, and then the maximum tension force is 750. So we're going to plug in 750 here, because if we want to get the maximum speed allowable, we want to be using the maximum tension force allowable. Okay, that's the reason we're doing that. We want to see the maximum tension force there. Any questions on this example? We've got a couple more to do today, so I want to keep going. Yeah, Isabella, go ahead.
So when you see force of 750, do you automatically assume that that's just FT, or do you have to take into account that that's like FG2?
So that 750 is FT, because what it says is the rope can withstand this much force. So it's the force in the rope which is called tension.
Oh.
Okay, that's physically how much you can withstand before it just snaps through the hole. So yeah, that is the 750. That is FT right there. Okay, FT is 750. And FT could be less than 750, right? If this person suddenly goes lower than 4.6, well, do the math. If you decrease this number, take a look where I'm pointing, please. If you decrease V in this formula right here, it's directly related. It's directly related to the square of V, really, but it's directly related nonetheless. So if you lower the value of V, what happens to the value of FT? If you lower V, go slower, FT is lower or less. Okay, I did that yesterday. Remember, I spun it really slow, and when I spun it too slow, it just eventually fell. There was no tension in the cable. But if I spun it really fast, you can not only hear it, but you can almost and you'll do this actually in the next class. We're going to do a lab on this. You'll physically feel the tension in the cable. So the faster you spin it, the more tension you're going to have. So 750 is the most tension can be, but it can be less. If V is less than 4.6, okay, then tension would be less. And try it if you need to. Go ahead and try. Pick a number less than 4.6, like 2. Plug it in here. And then plug in all the rest of your values you know, and you'll get an FT value that's going to be definitely less than 750. Okay? Definitely less than 750. Great question, Isabella. Okay, I didn't even think about that before. All right, example 5. So we want to look at a person that is exerting, a force on a string. The string is attached to a ball, and the ball revolves in a vertical circle of radius 0.75. When the ball is at the bottom of the path, the ball makes 1.5 revolutions per second, and then what about when the ball is at the top of the path? So what we want to do here is point out the fact that we don't have to do this twice. We're going to look at the free body diagram, and it's just going to change the equation of motion. There's going to be one major change that you already saw when we looked at that example spinning. The other part here is that we're given not the velocity, right? Not the speed, not the velocity. What are we given in this problem? What are we given here that's similar to an earlier problem? The frequency of revolution. So the frequency of revolution is 1.5 revolutions per second. So the time period it takes is going to be 1 over 1.5, and that's unit in seconds. We can use either of those variables when we're calculating speed. Okay, so the next part we have to recognize is that we're going to have to calculate speed. The radius of the rope is 0.75 meters, and the mass of the object is 0.12 kilos. So we've got those values given in the problem, and we want to know about the force needed, which in this case is again tension because it's a rope, the force needed to keep it in circular motion. So let's take a look again. When it's at the bottom first, we'll do that at the bottom first, and then we'll look at the top afterward. So when it's at the bottom again, we've got tension pulling up, and we've got the weight pulling down. And then we'll do the other one here at the top. So this is the bottom, and this is the top. When it's at the top, tension pulls back down, and weight always pulls down. Remember, FG is never going to change its direction, ever. Literally, ever. FG will always act down. Now, there are times, like on the inclined plane, where we break up FG into components, FGX and FGY. But FG, the overall force, your weight, always acts down. Always acts down. It's tension that changes direction here. And if you need to show yourself, draw yourself a diagram, right? Do this, please. If this helps, do that. And do this. Okay? Some students like to show the direction of the circle or the path of the circle because it might mentally help you to understand which way FT is acting. FT is the thing that is keeping it spinning. So it's got to act toward the center. So by drawing the circle, it might help you to remember which way FT acts. Whether it be up or down, it's always into the center of the circle. So in the first circumstance, we've definitely got FT acting to the center, FG away from the center, so minus, and that equals mv squared over r. And then in the second scenario, we've got them both acting toward the center, so it's going to be a positive in this case. Okay? So those are our two scenarios that we're focusing on in this problem. So I want to point out the fact that, yes, it looks like they're two different problems, but FG is the only thing that's going to change, and it's only its sign that changes. So this is why I keep talking about modeling and how important modeling is. You need to be able to model a problem and say to yourself, well, this is, somebody spinning a ball around. It's going to be very similar to when we get to a roller coaster going around that loop, with Fn pushing into the middle and Fn pushing into the middle. But at the top, Fg pushes into the middle. But at the bottom, Fg pulls out of the middle. Similar to this. It's literally the exact same problem as this, actually. Okay, except instead of Fn, instead of Ft, you put Fn. And you put Fn here when it's the roller coaster problem. So we're modeling. We're looking at a tether ball or something on a cord and a roller coaster and making them analogous to each other. Anyway, the point we need to figure out is what is V? Because besides V, we've got everything, right? Fg, I'm going to ignore the other one because they're the same. Fg is just mg. We've got m, we've got g. R is given, m is given. We're solving for ft, so really we need v, right? We need the tangential speed. And we've got two formulas we could use. So honestly, it doesn't matter which one you choose at this point. Can you give me the two formulas for v based on what we derived a couple slides back? Give me one of them, Jack.
2 pi r f.
Good, and the other one?
2 pi r over t.
Yeah. And it doesn't matter which one you use. Whether you put f in as 1.5 here, or you plug in 1 over 1.5 for t and plug that in here for the time. It's up to you. It's up to you. Can somebody give me a number for v? Can somebody give me a number? Calculate that quickly. 2 times pi times 0.75 times 1.5. I would probably use the top formula because we were given frequency, right? I think it's just easier to use it, but I solved for t anyway, which was 1 over 1.5 or 2/3, so you could use that as well. It doesn't matter.
7.07.
Can I get a nod? Yes? Thank you. All right, good. 7 point, not that I don't trust Valentina, but I always check our numbers so we don't do the wrong problem, right? All the wrong problem, the wrong number. So 7.07 sounds good. That sounds about right. And what we want to figure out here is where there is more tension and what that tension force is at the different location. So really we're just solving this for Ft 2 times. So Ft equals mv squared over r plus mg. I'm adding Fg over. And notice I'm doing this a lot. I'm going to, at some point in time, stop saying it. But when I move Fg over, I also replace Fg with mass times gravity. Because by definition, again, the weight of an object is its mass times gravity, so I'm adding that whole quantity over as mg. How does it differ for the top? Ft equals, for the top, Ft equals, how does it differ, Landau? Yeah. Okay, we're just subtracting the mg in that side. That's the only difference. So that's why this is very much like the elevator problem, right? We see that we're getting a value. In the elevator problem, it was Fn, and sometimes we added Ma, and sometimes we subtracted Ma. The same concept applies here again. What do we get for Ft in both circumstances? Give me the bottom. Give me the bottom. What do you got, Moro?
9.17.
Units? Can I get a nod? Yep, all right. How about the top? At the top? First of all, what will the answer be at the top relative to 9.17? Less. I said relative, right? Relative means greater or less than, I'm saying. So relative to at the bottom, at the top, it will be less because we are now subtracting mg as a value. Okay, what do we get at the top? What do we get at the top? George, you got it for me or are you doing it still?
No, I gotta do it.
Okay. I do want you guys to practice, right? That's why you should have your calculators out and be doing this. Practice makes perfect. Practice makes perfect. On the test, when you make a mistake, I'm going to have zero pity if you're not practicing. Vinny G, what do you got for me? 6.82. That sounds good. No? Yes? No? I got a yes from a couple people, right? 6.82. George?
Yeah, I got that.
Okay, check if you can get 6.82. Check if you can get 6.82. Okay, we know it's got to be less. It's got to be less than that value. Now, here's a question for you. Here's a question for you. At what point, how would we figure out the velocity that would cause the rope to go slack? To go slack. I use that phrase in it there, right? Slack. How would we figure out the velocity that causes the rope to go slack? What do you think?
You said Ft to 0, so I believe.
You hear that? Listen carefully. Set Ft equal to 0. Let's write this down. How to figure out the velocity that causes the rope to have no tension, to go slack. No tension means set Ft equal to 0. Okay, that would be the velocity necessary for there to be no tension in the cord. And that can happen. And I showed it to you guys. When I was spinning the mass around yesterday or 2 days ago, sometimes the mass would just start to drop and there was no tension in the cable. That's the moment where there is no tension or the rope goes slack. You should know that phrase, slack. Okay, it means no tension. Questions on example 5? I'm trying to really give you guys all the examples, right? So you really are aware of all the possible types of problems because they're similar, but they're just slightly different because they're analogous. Regina?
What were you saying about the slack? Is it 0 or how do you?
It's when you set tension Ft equal to 0. Because for there to be slack in the rope, it means there's no tension in the rope. By definition, slack means no tension. No tension. You'll use that phrase or you'll hear that phrase in your text also.
I know this is just for the top and the bottom, but will it ever be to like the right or the left or?
Yeah, to the right or left is another problem, and Fg would actually be acting perpendicular, right? Because think about it, if it's on the right, it's a great question, Jack. If it's right here, Ft still pulls into the center, but Fg acts perpendicular. So it does not affect the centripetal force, so this would just be not there. And so you hear what Jack is saying on the left or right side? These would just not exist, because they don't act toward the center. They act up and down. Okay, it's a bit of a different problem. We're going to tackle that more in AP physics. Okay, it's not going to be one that we're going to really be focused on here.
To solve for the top, I just subtracted, do the math, I just subtracted 2 times its weight.
You distract, yeah, that's a good idea. You hear what Valentina said? Because think about it, how did we get the tension here? We added on the weight, right? So we got to get rid of this weight and then subtract another weight of its value. So she just figured out the weight and subtracted twice the weight from this number and got 6.82. That works, absolutely. Good idea there. Very good idea. Okay, it works either way. It works either way. All right, the next example. So we're back to this problem finally, the one that I started with, that I had you guys think about how you felt, right, on this ride. So this is, I call this the gravitron, by the way. When I was your age, I guess it was called the gravitron. But your text calls it some weird name. Like a roundy round or something. I don't know what it's called. It's a weird name. I've never heard of it. I called it the gravitron growing up, and that's what it was always called. But it doesn't matter what it's called. So a rider on the gravitron with a radius of 5.2 rotates at 4 revolutions per second. The rider feels pressed against the wall, and the floor slowly drops out. Determine the coefficient of static friction that's necessary between the rider and the wall that keeps it from sliding down. Yeah.
Mine says like Ferris wheel. Like
Oh, sorry. I updated the notes. Oh my gosh, yeah. So that's your last slide right now that you guys have in front of you, right?
Yeah.
I updated the notes last night, so pause for a minute. I'll pause, sorry. Go to Moodle real quick. Open the notes, and from example 6 down, there's a bunch of other files. Yeah, there's 6, 7, and 8. The 6, 7, and 8 we're going to do stuff. Sorry about that, guys. That's why I said, remember I was like, the notes weren't finished yesterday? I changed it because the Ferris wheel problem was in your reading. And because you did reading this one for homework, I didn't include that problem because it's the exact same problem that's in your reading. So I got rid of the Ferris wheel problem that I usually talk about, normal force, because again, you read about it already. That's why I got rid of the Ferris wheel problem. And I changed it to this one because I think this is a little bit trickier and it's a lot more fun. Okay, we get to look at friction here instead of just normal force. You see normal force, but friction's involved too. I apologize. Thank you for the heads up. Yeah. You're like, wait, what's going on? This isn't right. So you should see example 6 now. You'll see probably then, I think I talked about unbanked turns, then example 7, then banked turns, then example 8, and then your homework should be on the next slide. So all that should be on your notes now. Sorry for that. Can I start it? We have 6 loaded by now, you think? Maybe? Are you loading it still? Still loading it? Yeah? Sorry. I'll start talking as people are loading, okay? Here's what I'm going to do. I'm going to start with a free body diagram. And watch the way I'm going to draw my diagram, please. For this problem, it is useful to kind of draw yourself the cylinder. Okay, draw the cylinder first. And this is the gravitron right here. This is the gravitron. Now, you are here. Okay, you're up against the wall. What pushes you back into the center? When you want to move outward, what pushes you back into the center? We spoke about this last class, and a couple of you knew it right away. What force, remember, what force always pushes away from a surface perpendicular to that surface? The normal force. So we've got the normal force pushing into the center there. Okay? But we also have other forces at play. What wants you to fall down or wants you to move down, right? The floor, there's no floor beneath you. The floor drops out. Everybody, what force is that? Gravity. Gravity always pulls you down. Always pulling me down. Man, what a drag gravity is, huh? Always bringing me down. What force reacts to gravity here? What force keeps you from falling down? What is it? Static friction. So here's what's going on in this problem. And it's a little bit tricky because of the free body diagram. So we want to consider the fact that we can have some of the forces in the x direction, some of the forces in the y direction, and some of the forces in circular motion or in the radial direction. Well, unfortunately here, it seems like Fn is in the x direction because of the way it looks, right? But Fn is actually in the radial direction. If I were to draw the same circle, but from a bird's eye view, from above, this would be the person, and this would be the normal force. That's what the bird's eye view would look like, or aerial view, right? Or top view, you could say. Any of those are acceptable. Your book might say aerial view, top view, bird's eye view. When looking from above, that's what the free body diagram would look like. I can't really draw F friction and F for gravity on this one, because one of them, friction, is out of the page, right? Think about the way friction is acting. It's acting upward, which is out of the page. And which way is gravity acting? Into the page. Gravity is acting toward the ground. And if I'm a bird looking from above, right? Imagine you're a bird from above. The person would want to fall down, which is in this case into the page. So gravity acts into the page, friction acts out of the page. So it's really tough to label the forces in a bird's eye view, which is why we draw it like this with the cylinder. Is that clear? Okay? But it is nice to see this here still. So as a result, we can take a look at our equations of motion here. our equations of motion are twofold. We've got sum of the forces acting toward the center equals mv squared over r. That's the first one, and that's coming from Fn. And then we've got sum of the forces in the y direction equals ma in the y direction. What is a in the y direction? What is a equal to in the y direction here? What value is a equal to? George?
0.
How come, George?
Because you're not going up or down.
Yeah. Remember, the person is not sliding. Here's the statement right there, highlighted in red. That's the key. What's highlighted in red allows me to set a equal to 0. That keeps people from slipping down the wall. So you are in a state of equilibrium. Equilibrium. We're going to get there by the end of the year. When I say you're in a state of, the answer is usually equilibrium. Equilibrium. So in the y direction, we've got friction acting up. We've got the weight acting down. And that equals 0. In the radial direction, we've got the normal force pulling into the center. Anything else to the center? No. There's nothing. Look at the bird's eye view. The only force that is keeping this U in circular motion is the normal force. And since it's acting toward the center, it is positive. There's no minus anything here, and that just equals mv squared over r. This is never going to be 0, by the way. It's never going to be 0. You know we set this equal to 0 a lot, right? If it's in circular motion, there is some desire to move outward. That center fleeing desire, that centrifugal effect. That's mv squared over r. So whenever it's in circular motion, you're going to have mv squared over r. It's never going to turn out to be 0. Is that clear? Okay, I shouldn't say that. Unless v equals 0, but then you have circular motion. If v equals 0, it's not moving, so therefore there is no circular motion, right? So if you want to say, oh, when v is 0, that's nothing, or when there's no mass, it's 0. But if there's no mass, then there's nothing moving. So it's like kind of, catch-22 here. These are 0, the whole thing is 0 because it doesn't exist. So there's always going to be something on the right-hand side. And on the left-hand side, though, it's whatever provides the centripetal force, which is the normal force here. So why is it important that we write down both equations here? Who can figure it out already? Look at the equations. Start to mentally, take it apart. Dissect the equations. Find the variable that we're looking for. What is the variable that we're looking for, Juliet? Why is it important?
You need normal force to find the coefficients.
Very good. This is really mu Fn, isn't it? We've done this a couple times already. Fn is going to, again, be your linking variable. So in the y direction, I'm going to replace things. Mu s Fn minus mg equals 0. So, you know what? Hey, let's say we're a little bit overwhelmed and we don't like to use variables, we want to plug in numbers. Is this a problem that you can plug numbers into? Can you plug numbers in right now and solve? I'm saying, yeah, sure, you can solve. So what's Fn going to be when you plug in numbers? Give me a value for Fn. Ooh, can you actually plug in numbers here? I'm seeing a lot of looks like them, actually. What's going on, George?
I don't think you can because Fn is going to get substituted and F is going to drop off.
And is M given in the problem, George? So if you want to try and find Fn, you're not going to have a value for M. Do you see that? If you wanted to find the number for Fn and then plug it in here, you can't because you don't have mass. But as George mentioned, he's noticing already, by plugging in mv squared over r here, mass cancels out because it factors out and divides into the 0. Very good, George. Okay? Again, we cannot find a value for Fn. So we have to use substitution principle here. And as a result, let's see what our equation becomes. We get mu s times mv squared over r minus mg equals 0. Now, are we even given v in this problem? No, we're not. We're given the frequency. I'll put our givens at the top up here. We're given this. 4 revolutions per second and a radius of 5.2 meters. So, you know what? Let's go one step further. Let's substitute in for v now. What is the expression for v if we're using frequency and not period? If we're given the frequency and not the period, what goes in for v? From the last 2 problems, 3 problems, 4 problems. Thanks, guys, who are raising their hands. Go ahead.
2 pi RF.
What is it?
2 pi RF.
2 pi RF. Very good. I'm going to cancel mass at the same time. Okay? If you're not sure why mass is canceling, you've got to think about algebra. Factor the mass out, it's in both terms, mass comes out in front, and then divide both sides by m, and it drops off. That's the case for all these problems. When m is in every term, or there's a 0 or m in every term, it drops off. So our answer from US is given here. Okay, we could solve from US, move g over by adding it. Right, g is going to move over by adding it over. Then we're going to multiply by r, and we're going to divide it by 2 pi r f quantity squared. That's what the value of US will be. And yes, I know that r is squared here, and then one of them will cancel, so you can simplify. But then it becomes 4 pi squared f squared, so you can do that also. It's 6 and 1/2 dozen. It does not matter if you distribute the square, cancel the r, and then evaluate, or just evaluate at this point. Why can I evaluate at this point? Why can I evaluate at this point? How do you know when you can stop and just evaluate? Come on. What's the one reason, Juliet? You have all the variables. G, 9.8. R, whatever it was, I missed it. F, I missed it again. I think it was 4. F was 4, right? R was something else?
5.2.
Okay, so let's plug in and let's get a value here. Let's plug in and let's get a value here. I'm going to rely on you guys to give me a value here. What do we get? What do we get? Jack, what do you got?
0.003.
Agree, disagree? And this is one of those times where on a test, when the initial directions, I put like round to the nearest tenth, and then specific in a problem, I say something like, round to the nearest thousandth for this problem. That's why. Because rounding to the nearest tenth doesn't make sense here, right? So even though that might be a direction for the overall for response part of your test, please, when it comes to the coefficients of friction, things that are really, really small, keep a bunch of decimals. Because it doesn't make sense if you write this as 0.0. So there is some friction necessary, but is there much needed? No. Here's a question for you. When you guys go on this ride, are you actually strapped in? Yeah, you don't have to be strapped in. And what people will do is, they'll like rotate their body, so like this, and they'll start to turn. You can do it. I mean, I say that with no liability in case you fall. But you can finish the thing upside down.
I don't know.
Yeah, I know, crazy. If you get your body to move around fully, you can. Friction is enough because you're getting sucked out. So if you just keep pushing yourself with a little more friction, you'll start to turn your body the whole way.
I've done it sideways.
Yeah, sideways. Maybe don't go upside down. Just go to sideways, then go back.
But then, like on the Graviton at art school, the things, like the panels on the wall, like each move up and down on their own. So like,
Oh, they slide up and down.
So like some of your body like moves up and the other.
Yeah, interesting.
One time we were on it, like all of us, like a few other of our friends, and then he got sideways, and he turned the lights on and stopped the music and kept us in there. I know, it was so. Oh, he turned the lights off and stopped because you guys were. Yeah, we were gonna keep testing the music. Like we recorded it down.
How old are you guys?
We were like in separate, he was like 30 and yelling at us.
That could be pretty mean, huh? What? How much time do you have
He's
left?
gonna chill. I literally couldn't do it.
So let's start talking about this one. We're probably going to run out of time as we get into the beginning of the problem. Let's talk about it. So we're going to talk now about turns with cars. We're going to talk about unbanked turns, which is the easy problem. And then we're going to talk about banked turns, which is probably going to be the hardest problem type from this chapter. Okay? The banked turns, I know. Banked turns are pretty much just as difficult as this problem here. And we haven't even done this problem yet. Okay, tether balls have been going around at an angle. But I think one of your problem sets or homework that I asked you for this, or for this chapter, is going to involve this problem right here. Okay, but the unbanked turn is the easy one. So we'll start with the easy one for today. Next class, what we'll do is we'll look at the banked turn problem, and then we'll do a lab. And the lab you guys are going to do is it's a really cool lab. It's actually the analysis of that problem right there, the big problem. Okay, and you'll see how it plays a role in the lab. So we'll do that, and it's a hands-on lab you're going to physically do yourselves. So we'll start this off just so we get a little headway here. So the car's going around the turn, The car is going around the turn, and because the road is unbanked, it's not like, you're gonna need a bank turns, by the way. NASCAR, you ever watch NASCAR or anything like that? When you go around a turn, the walls are kind of banked, and then they go flat afterwards and they go straight.
I was gonna say, is that so like it's fly off the track?
Yeah, bullet trains do, entrance ramps on highways do. I was driving this weekend for the Camden trip, and every entrance ramp you see is literally a bank turn. And that banking of the turn actually is God bless you, is a really, really important thing, the banking of that turn. Because there are times when the road is wet, and there's almost no friction. The banking of turns on highway entrance ramps is enough to keep you in circular motion without any friction at all. So if you literally were to have no friction because it's wet out, it's not necessary to have it because the banking provides enough of that counter force into the center. We'll see more of that in the next class. But unbanked turns, what we have is, again, a car from above. I'll draw the view. There's from above. Here's the car at the bottom going this direction. Okay, that's why this continues like this. There's the road continuing. When the car is here, the force acting toward the center, that's not a great force, sorry. Towards the center, I should draw it a bit better here. Okay, toward the center. That force is friction, and it is static friction. Again, it is static friction. Now, notice, zoom in on the diagram. If our question in the homework talks about the force of friction on the tires, then that's what we're going to use. But, and this is when we're looking at the car. But if I'm drawing a free body diagram of the person, what keeps the person in circular motion? What force acts on the passenger? Notice the difference? The force acting on the passenger is much lower than the force acting on the car. What's the force acting on the passenger? When you slide into the door, why don't you go out the door? What is it? What force? The normal force. It's the door pushing back against you. So depending upon the problem, if the question says, find out the value of the force keeping the person in circular motion, we're looking at the normal force. And instead of using mv squared over r, where m is the mass of the car, we would use the mass of the person. Do we all see that? And is the mass of a person greater or less than a car? So this force, Fn, is going to be less. So look at my diagram here, please. Notice the length of the vector for the person or on the person is much shorter than on the car. That's the reason for it. Okay, so here's what I want you to do. Your homework will not be due next class yet, because we're going to start a lab, we're going to do a little more of bank turns. But I already have the homework assignment there. I highly recommend that you start the homework assignment over the weekend, and you do as much as you can. Pretty much everything besides bank turns you can do at this point. The homework is up, and I put the problem set up for this section. So please, do yourself a favor, get a head start on the homework over the weekend. Okay, I might even send you the lab over the weekend so you get an idea to read through it. I got to start doing more of that so you can get a pre-lab.